Okay, well, good afternoon. Um, this is the last week of classes, so we have made it past this crazy semester. So who knows what the fall will hold? Hopefully face to face, but I don't know. I guess we will see. So this week I'm just planning to take your questions. Really, I'll kind of flip through the past PowerPoints and kind of go over things that um, I'll focus on for the final. But yeah, basically, this is your opportunity to ask questions about the concepts as we go through them. If you want more examples, we can do that. But it's really, um, yeah, I'm here for you to answer your questions. I haven't yet made up the final exam. I put together some questions, but it's not finalized yet. It's many more than this list. I think it's like 80 something questions, so I have to narrow it down. But this is how it will shape up. So next week, the final exam, I'm thinking of kind of getting it to 50 to 55 in that range of total questions. The chapters, it's cumulative. And so it's over all the chapters we went through, so 1 through 5. Um, I can't remember if, so I said you can use 8.5 by 11. Did I say both sides or just one side of it? I think I know what you're going to tell me, but yeah, okay. All right, so yeah, so you can use, yeah, both sides of eight
I
and a half
swear
by,
you said both.
oh, pardon? Sorry.
I swear you said both.
Okay. Yeah, LOL. Okay, yeah. Yeah, you can definitely use both sides. And then a periodic table. I'll try to put one on the exam. I have to figure out how to do that for this stupid browser thing. I'll try to put the exact one that you used before on there, but you're free to use the one that you had for an earlier exam anyway. So if you want to print that out again, or if you have a copy of it, feel free to use that with the names and symbols of all the elements. And any type of calculator will also work. Okay, so during your webcam check, I know who you are, so when it says to hold up your ID, just kind of hold up your periodic table and the sheet, something like that. If you hold that up, that'll work for it. Okay, and then I'm thinking of giving you more flexibility too. So I think it's scheduled for next Wednesday, but I'm going to open it up so you can take it any time in the block, all day Wednesday or all day Thursday if you want. Okay, just to give you, I don't know how your other classes are with their schedules, so just give you, more flexibility. But the link will disappear at 11:59 on Thursday, so take note. And then I'll also give you a lot of time, a lot more time than what you need. And so, I'll give you the time that, a modern Scorsese film is these days. So 3 hours, how about? Okay, so that should give you plenty of time to do the exam. Okay, so questions about the formatting of it? Okay. As far as we're gonna kind of go through the concepts to really look back on today. I haven't verified. I'm not sure if the Blackboard practice midterms, if they're still available or not. I'll double check that. If they're not, then I'll. Oh, they are. Okay, cool. So you can. So you're able to take them yet, or have they expired? So I don't know if you can. They may be visible, but if you try to click on them, it may not let you attempt it. I wonder. Okay, you can. Okay, cool. So really your best way to study would be, look through um, these PowerPoints, especially, the sections I'm going to go through with you this week. Um, and then those practice midterm assignments, because that's it's actually even better than the ones I put on Connect, which kind of go, they're similar questions, but a little different. The pool of questions I'm drawing from for your final are exactly those that I pulled for these practice midterm uh, questions. And so, if you look through those, so the practice midterms as well as your actual, midterm exams, I gave back your first one or two. I can't remember before all this stuff hit. But you've got your physical exams from earlier in the semester you can look at. And then, what is it, the last two maybe? One or two. You can look at the videos, the WebEx videos for the solutions for those. And so again, you may have the exact question from those on the final. So I'll I have to look back to remind myself what I already asked, but yeah, they're all coming from that same pool. So the questions should be very, very similar to that. Okay, and then what I'm going to do is post a few additional questions related to topics that you haven't had on exams yet. So that is related to shapes. I think the last exam stopped at Lewis structures. Did it not? Do you remember? Did you have VSEPR yet? I always get you confused with my big class. I can't remember, and they've had all this. I can double check anyway. So I guess yeah, the topics since your, so I'll just put it this way. So topics since your last midterm. Okay, so that's definitely energy calculations. Okay, things like how much energy does it take to break apart molecules, or remember when we had balanced reactions, then you had to add up all the bonds that are being broken, all those that are being formed, and then do all that stuff. So definitely that type of calculation, as well as I think shapes is on there too. But okay, so I'll just post that on Blackboard too. So it'll just be I'll label it I don't know, additional questions or something like that. Okay, so any questions before we kind of get into content here? Okay, all right. So let's talk. Let's go back to chapter 1. So back in the days when we were together in the classroom. So chapter 1, there's a lot of this that I really won't be focusing on, and so I think this week is going to be good to really help you focus a little more. So definitely so if I make a list here, definitely the periodic table, um, knowing names of groups, and in particular it's groups 1, 2, 15, 16, 17, and 18. Okay, so we've got the alkali metals, the alkaline earths, the pnictogens, the chalcogens, and then the halogens and the noble gases. Okay, so those names. This slide, kind of shows you where the names come from. The periodic table you can use will have the name and symbols, so it's not something you have to, really even memorize. Okay, so that won't be an issue for you guys. Um, I guess the difference between periods versus groups on the periodic table. So, a period is a row, a group, we're talking columns. The metals versus non-metals. So this one's color-coded. The periodic table you'll be using is not. And so kind of remembering which ones are metals. So most of the periodic table are metals. So for sure, all of group 2 and most of group 1. So remember hydrogen, it's here in group 1, but it actually, most of its properties are shared with the group 17s, really. And so I don't know if you remember, but in the classroom, uh, hydrogen was listed over here, sort of right beside helium. Okay, so yeah, most of this, so all the green are the metals, so all the lanthanides, all the actinides are metals, and then you've got all these pink ones that are metalloids or semiconductors. Okay, so that means the same thing, really. And so boron, silicon, germanium, arsenic, antimony, tellurium, and then, these ones are not used for any application. So kind of if these ones, so 1, 2, 3, 4, 5, 6. So if you know those 6 are metalloids, then, you're in really good shape. Okay. Um, what else about the periodic table? I guess realizing that these groups, so the lanthanides, fit right in here. Okay, so the atomic number, I guess that's the other thing. So atomic number, so they're arranged, all the elements are arranged by atomic numbers, so that's these numbers here. So it goes 57 and then 58 through 71 and then back to 72. Okay, so it's inserted there. And then the actinides go right in here. Okay, so this is where they're inserted right there. Let's see. Oh yeah, and then the elements that are diatomic. Okay, so we went through this ad nauseum this semester, so I'm sure you know this, but it's just these. 2, Cl2, Br2, whoops, and I2. So there should be, did I miss any? Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, yeah. 5, 6, 7. 1, 2, 3, 4, 5, 6. Yeah, there are 7. Okay, I can't count today. Yes, there's just 7 elements that are diatomic. Okay, so in other words, if there will be some questions where, I put in words, like carbon reacts with nitrogen gas to form carbon nitride. Okay, and so you would say carbon plus nitrogen gives you carbon nitride. So what do you think? Yeah, what would the formula be for carbon nitride? So do you remember? So for those, you have to consider the charges, right? Based on what groups they're in, and then try to get the total charge to 0. And so the charges, group 1, it likes to be +1. This likes to be +2. Then we're over here. You skip these ones because they're multiple charges. They can iron can be +2, +3, +4. And so we kind of skip these, and then we're here. This is +3. And then carbon is where you start to have kind of two possibilities. So the group 14 can either be +4 or -4. Okay, and then nitrogen, this group, the group 15s, can be +5 or -3. And then we kind of are back to what you can predict more easily. Okay, so those are kind of preferred charges here. All right, so based on carbon nitride, so carbon is going to be on the left of the formula here. And so that means it will have a plus charge. And so it's going to be +4. And then nitrogen is going to be on the right side of the formula. So that's going to have a minus charge. Okay. So now what do you think? So those are their charges. So how can you put those together so that everything is a zero charge? So like that? Does that work? How about that? Yeah, so yeah, right. C3N4, right? So now you've got a -12 and a +12 as far as charge. Yeah, so C3N4. Okay. Um, yeah, all right. So that's periodic table. Those are names. Classification of matter is really important too. So not really anything to do with plasmas. So, really in this class we focused really on three states of matter. So solids, liquids, gases. And then knowing what the pure substances are. So either elements or compounds. And then mixtures can either be heterogeneous or homogeneous. Okay, so homogeneous, like a solution, is an example of a homogeneous mixture. Like if you have sugar and water, for instance, that's homogeneous. Heterogeneous would be like soil in your backyard or something, just a mixture that's not evenly distributed. Okay. Let's see. And so there will be some questions, probably a couple, where give you something and then you have to put whether it's a mixture, compound, or element. Okay, and it might even ask a little more specific of heterogeneous or homogeneous for mixtures. Okay. Law of multiple proportions. This, it's kind of it's a definition, but it's not something I would ask per se on the exam. Like, what's the law of multiple proportions? This is just really realizing that the elements can combine in different ratios. Okay, and so you have just these whole number ratios between the elements in a compound. Okay, and so these would be two different compounds. Okay, since they have different ratios, and then their properties would be different. Okay, so that's kind of the definition of compounds, is that you have, so you should really know for sure definitions of what's an element, compound, mixtures, and then you've got homogeneous, heterogeneous. Okay, so for sure those definitions. And then, yeah, so compounds, composed of two different elements in different ratios and they'll have different properties. Okay, whereas an element has really just one type of atom. Okay, these have two or more different types of atoms. Okay. All right, and then this one gets in a little more detail. So elements are composed of mainly atoms, but you could have, so there are those seven. So these ones, for instance, where are they? Right here. Okay, so these elements are composed of molecules. Okay. And most of the time, like if you say carbon or some of these other elements, they're really composed of different atoms. So element is different carbon atoms arranged differently in 3 dimensions. And so remember, you could have like different ways that carbon atoms or any atoms can be rearranged to give you different elements. And so, for instance, carbon has graphite, diamond, and then that's, those C60 or C72, what are called the fullerenes. So just think of these as like those soccer ball varieties, okay? And so in each one of these forms, the carbon atoms are arranged differently in 3-dimensional space. And so these are called allotropes. Okay, so it's just different structures of the elements, okay? So then different types of compounds, and so we're going to talk about this in later chapters in a little more detail, but you've got the molecular compounds and ionic compounds. And so then that goes to, when you're naming these, they have different rules for naming. And so molecular compounds are ones where it's non-metal with a non-metal. So compounds. Ionic is a metal plus a non-metal, and then molecular are 2 non-metals. 2 or more, I guess. Okay. So any questions so far? So just the really classification of matter from this chapter pretty well. Okay, and then we got into the structure of an atom. Okay, and so atomic structure is important. Not really knowing these values at all, or even relative mass, the charges are the most important things. And so atomic structure, knowing electrons, protons, and neutrons. Okay, and then knowing what their relative charges are is important. Okay, so the neutrons neutral, positive, protons are positively charged, electrons are negatively charged. And then looking at atomic structure, the nucleus has protons and neutrons, and then electrons are outside somewhere, okay, in different orbits, okay? We then got into talking about isotopes, okay? So allotropes, isotopes, make sure you know the difference. So very different. I mean, they sound similar, but they're very different terms. So allotropes, just how do carbon atoms arrange differently to give an element, okay? Isotopes are really detailing atomic structure. And so these will differ by the number of neutrons in the nucleus. Okay, and so remember there was the symbolism that we used. So you could say for isotopes really two different things. You could say this, so carbon 12, you could say that, or you could say this. Okay, so that's the two different ways I could illustrate or, put a isotope on the exam. Okay. This refers to the mass number. Okay, and so it's essentially that top one. So that's the mass number. And so that's your neutron, whoop, can't spell, neutrons plus protons. So essentially, most of your mass is in the nucleus. And so the mass number is all the things at the nucleus. Okay. And then that's your atomic number at the bottom. So that's just your number of protons. Okay, and for neutral atoms, the atomic number is equal to the number of electrons also. Okay, and so let's do practice here. So what about, and then, so let me pull up a periodic table here too. Let's see. Okay, so carbon is here. So the bottom number is often left off too. Okay, so this, whoops, you can't see that. Let me move this over a little bit. Okay. Well, there, 12.6. Okay, so this isotope symbol could be illustrated as just this. Okay, because since you already know the symbol is carbon, you know that it's element number 6. Okay, so those mean the same thing. Okay, so how about, what if I give you a question like this, where that would be the harder variety. This is the really easy one. Okay, so I'll do that one, and then let's do this one where I guess, it's probably, So on an exam, if I give you one like this, I'll give both numbers then. Whoops, you can't see that. So what is X? So this is really as easy a question as you can get, right? Because this bottom number tells you what element it is, right? So this is 15, so you just literally look, okay, what's element 15? Oh, it's phosphorus. Okay, so it's really phosphorus 3215 would be the full symbol. Okay, does everybody see that? So just look at this bottom number, will tell you the identity. Okay. All right, so now with this symbol, tell me how many protons, neutrons, and electrons does it have? So how about protons first? How many protons?
15.
Yep, 15. So again, that bottom number. Okay. How many electrons? Yeah, same number, right? Because it's a neutral element here, so it has to have the same number. Okay, and then what about neutrons? 17, yeah. So neutrons, you always do this number minus that number. Okay, the top minus the bottom one. Okay? If you had this one, what is that? I'll just do like this. Okay. So I'm leaving the bottom number off there. Okay, so protons, what do you think? No, so protons first. Yeah, so protons are the bottom number that I've actually left off here. Okay, so if I leave it off on the exam, by all means, on a scrap piece of paper or something, you can write it in. Okay, so it's element 7. Okay, so that means that there's 7 protons. Okay, how many electrons in this case? Yes, yeah, there are 3 more, right? Because that's a -3 charge overall. Yep. And then neutrons is the same as what we did before. So that number minus that one, so it's 7. Okay. And then positive charges, would have 1 fewer. Okay, calcium 2 plus, that would have 2 fewer electrons than protons. Okay. All right. So where were we? Right here. Okay, so atomic structure. Um, Electrical conductivity is not something we really talked a whole lot about. I guess knowing that metals are electrically conductive, so they're, I don't know. I might have a question where I give a series of elements, so maybe I'll do this. So let's see. And selenium. Okay, and then ask which one of these would be electrically conductive. So what do you think here if we do a little multiple choice here? Yep, yep. So you're looking for the metal, right? So calcium is in the group 2, okay? So yeah, something like to that effect, I guess, but not in any big detail here. Okay, and then this won't be on. Probably really the only other big concepts from the chapter then would be Sigfigs, big time. So look for a couple questions. One where you have to, what's the number of Sigfigs in a like a number? So what about this? How many Sigfigs does that have? Yeah, so I'm seeing, yeah, so 5, yep, yeah, exactly. So all of these are significant. And then this is really the only case where it's kind of difficult, right? Um, in that case, how many sig figs does that have? Yeah, just 3. Yeah, and so the easy way is write it in scientific notation. Okay, and then that tells you that there's 3. Okay, So yeah, so number of sig figs could be a question, and then like some mathematical operation. Um, for instance, how would you express this number? Well, that's probably too easy. What about this? Yeah, what about that? That's a better one. Okay. So how about this? 42.23. What do you think? Is that correct? Yeah, so yeah, remember the operations for addition, subtraction. It's all about the decimal places. So that has one decimal place, that has two. So your answer should only have one. Okay, and then you'll have to round appropriately. So this is, that's smaller than 5, so it really should be 42.2. Okay. If these were being multiplied, so 42.1 times 0.13, now it's all about sig figs, right? So that has 2, that has 3, so your answer should be to 2. Okay, so what is this in the calculator here? So 42.1 times 0.13 is 5.473. Okay, but to 2 sig figs, it is 5.5. Okay, so yeah, be aware of those rules for mathematical operations too. Okay, and then um, scientific notation. So none of this stuff is going to be on any of the reactions. Then just really scientific notation. Okay, so that would be very small numbers have a negative exponent, so it'd be 1.5 times 10 to the minus 6. Okay, whereas really large ones have positive exponents, right? So it's 1, 2, 3, 4, 5, 6, 7. Okay. All right. Yeah, none of the stuff related to like how are chips made, all that stuff. I'm not going to ask any detailed questions either. Um, Really, this. So as far as like the context pieces, this slide for sure. So the 3 pillars of sustainability. So knowing, some examples. So for instance, remember when we were face to face, we were looking at the 3 pillars of sustainability applied to like solar versus, I think we did like electrical generation using solar versus burning a fossil fuel or something like that. Okay, burning coal, I think it was. Okay, and so we looked at all these different pillars. So, kind of, look back in your notes, and there may be an applied question related to this. Okay, but knowing what are the 3 pillars, and then, what kind of would fit under these pillars would be kind of one question that I'll put on there. Cradle to cradle versus cradle to grave. Okay, so those recycling, knowing the difference between them, kind of the names suggest what they are. So, cradle to grave is where you unwrap your new cell phone and throw the packaging in the trash, versus cradle to cradle is you then would use the box for some other application. right? So it's going to dovetail with the beginning of another product. Okay. Um, yeah, the rare earths. I guess knowing what are the rare earths. So they are scandium, yttrium. So these ones, and then lanthanum, and across this series. Okay, so the lanthanides as well as scandium, yttrium are the rare earths, and just kind of knowing um, where some applications are. So you don't have to know this whole list, but um, a lot of advanced um, technology rely on these, and so kind of knowing that they're used for a lot of our advanced electronic applications, but they come from essentially one country in the world, and so that could lead to problems. With pricing, for instance, who knows now with this whole COVID-19 if countries around the world kind of gang up on China because the thought is that it started there, although there's other stories that could have even started here. Who knows? But let's say it started in China, and then we all get upset with them and want to put tariffs on them. They may say, okay, I'm not going to send you any more rare earths, and then what are you going to do? So we won't be able to uh, build any more windmills because that relies on a lot of rare earths go into the mechanism to turn the windmill even, or microphones for any electronic that we have. So a lot of things will just be shut down, and so anyway, so it kind of could lead to a lot of things. Um, all right, and I think is that the last slide chapter? Yeah. Okay. So those main concepts then. So the rare earth elements. So what they are, identity and applications. Okay. So any questions about chapter 1 then? What are important there? Okay. All right. So chapter 2 was dealing with air quality. And so so really the regions of the atmosphere, the two big ones to know, I really don't care about like thermosphere, mesosphere, all these ones. Stratosphere, troposphere are the big ones. Okay, so this is where we live. Okay, the troposphere. This is the ozone layer. Okay, so that's kind of like chapter 3. We talked about that layer. Okay, so that's why they're important. Then talking about air as a mixture. Okay, so it can be a homogeneous mixture if we're talking about just normal air. Okay, but it could also be heterogeneous, like in a dust storm or something like that, right? So if you have particulate matter, okay, so knowing what PM refers to, okay. Knowing, I guess, this is kind of interesting. So this group did a survey of what Americans know about science, and it was less than 20% of the population knew that nitrogen makes up most of our atmosphere. So please, don't be one of those in our society. If you go into politics or whatever, make sure you realize that, nitrogen is actually most of our atmosphere. So 78% nitrogen, 21 oxygen, then you've got those others like, CO2 or argon, other gases. Okay. Yeah, this I guess knowing that some gases are unreactive, so nitrogen, whatever you breathe in, you breathe out that same amount. Same with argon too. But oxygen is used for respiration, right? So you breathe it in, and then less comes out because it's actually reacting. Okay, and then CO2 as well. Okay, so most of what we breathe out is going to be nitrogen with oxygen, but there's going to be more CO2 in our breath than what is in the atmosphere. Okay. And then water is the only one that's variable because, it depends if you're here, maybe not so much water in the atmosphere versus Houston, Texas. It could be, like 90% or something humidity. Okay. And then, what else is in a breath? And so those were like the pure gases. Okay. So really, like this one shows kind of what pure atmosphere, what pure air is. And then what else we can put into air to make it dirty. And so those are these gases. Okay, so NOx means NO, NO2. Okay, and then SOx are these two. Okay, and this gives it, so there's brown haze in Beijing here. That's this one. Okay, NO2. And then a whole bunch of particulate matter. Okay, so there's PM 2.5 or PM 10, and so these refer to microns. Okay, or sort of the average size of these particulates in the atmosphere. Okay, so PM 2.5 would, on average, those are the size 2.5 microns. Okay. All right. Air inversions. I guess being familiar with the term. So, what is an air inversion? And just think, these mountainous places like Phoenix, Salt Lake City, where you've got mountains surrounding it. And so you've got all this trapped pollution because of the mountains. And now you actually have warmer air that's above the cold air that kind of keeps all this pollution trapped in here. So that's called air inversions. Okay, normally cold air is higher than warm. Okay. All right, and then we got into chemical formulas, and so the different ways we can illustrate molecules. And so, we talked about particulate, where you're actually showing bonding, and we looked at different shapes later on. So this is water; it's bent, okay. Whereas that's just the symbolic; it's just H2O, okay. Not, I wouldn't really ask definitions per se, but just knowing, I guess, what a chemical formula is. Okay, so like this, whereas a molecular representation kind of shows how they're bonded together, whereas a chemical formula doesn't show how these are bonded. Okay. And then we have different color codes for these. Not something I would ask on an exam, but I guess this comes in kind of later, right? That you would know for CO2, that it's a linear molecule, and the Lewis structure says you've got a double bond there. Okay, so kind of not much with this slide in this chapter, but I guess knowing this for later on. Okay. And then our first naming came all the way 1 carbon to 10 carbons. And so knowing how to name different, I guess these, so we're not there yet, I guess. So these are just for, prefixes for binary compounds. So these were, so naming molecular compounds. Okay, and so that's nonmetal plus nonmetal. Okay, and there you have to use these prefixes. Okay, so that's, I guess the only time you don't would be for this. Okay, so you don't say that that's mono. Okay, so if there's one of this one on the left, you just say carbon, okay, and then it's dioxide. So this is carbon monoxide, okay. All right, and then some examples there. Okay. And then, oh, here's, yeah. So then also naming hydrocarbons. Okay, and that's where you had a lot of these prefixes are the same, except these ones. So mother eats peanut butter. Remember meth, eth, prop, and bute. And then beyond then, it's the same, right? Pentahexa, all these. Okay. All right. And the only ones you're going to be naming have an ANE ending on them. And they will all be like CXH2X plus 2. Okay. All right. And then concentrations. Add in paper here. There we go. So concentration units, you should know the difference between a ppm, so go back and forth to percent, okay? I probably won't do much with ppb, so this, the question on the exam would be really related to this, okay? So a ppm to percent, okay? So this is really part per 100, this is part per million, so you've got that factor of 10,000 in here, okay? And so this is a really nice kind of summary slide. So 21% or 21 parts per 100. So then you're looking at 210,000 parts per million. So to go from percent to ppm, you're moving the decimal to the right. Okay. Okay, and then vice versa as you're going back the other way. Okay, so you get that factor of 1 times 10 to the, what is that, 4? Yeah. Okay. And then, a question like this, per se, really fits in well with your QR designation for this class, so 265 QR, quantitative reasoning. I might throw in a question related to, maybe giving some data like this and then asking which is more toxic. Okay, so maybe just between these two. So nitrogen dioxide versus ozone. Okay, and then you having to kind of sort out that, in 8 hours, you can tolerate kind of this percentage versus, annually, you can only tolerate this much. Okay, so knowing kind of, we had that discussion, I think, in class when we were face to face, like which is quote unquote more toxic. Okay, and so the smaller the value means, it's more toxic, right? You can't breathe in as much of it in a certain time frame. Okay. Right. Risk assessment. So, there's, I guess this slide really is important. So risk assessment, you have to look at exposure and toxicity. Okay, so how toxic it is, like from the previous slide, numbers wise. And then you have to look at exposure. So like your breathing rate and length of time, all that goes into how risky is it to go into a certain place. Okay. Another one that, I may put a table of, or this graph on and, ask, calculate the percent decrease in lead between 2009 and 2014 or something like that. Okay, so just, kind of extrapolating these values and then just figuring out what percent decrease it went. Okay, so something like that where I actually show data could be on there. Um, yeah, the air quality index. I'm not going to have you memorize these. What's unhealthy versus very unhealthy. These numbers. Just, I guess, know CMU colors is the worst. As you're getting closer to CMU's colors, the air quality is getting bad. Okay, and so green is go, right? That means that it's really good air quality. Okay, and so again, I might give you a map of one part of the country, and then ask where is the air quality the worst or something like that. Okay, so you're just looking at really colors. Okay. And then just setting up chemical reactions. Okay, so what are reactants? So that's the left side of the arrow. Products are the right side. Okay, so knowing the difference between those two. And then we got into balancing. So I guarantee you there will be quite a few balancing equations. Some where it's just, you know, balance it and then nothing else. Others where, you're calculating, you have so many grams of this, you want to know how many grams of that, so you have to first balance it. So there will be quite a few related to balancing. And some I might put in terms of words too, right? So I could say carbon reacts with oxygen to give you carbon dioxide. What is its balanced reaction? Okay. So the strategy, I think you've done it quite a bit through the semester, so this is probably not too bad. Um, these, application questions, I won't ask any questions about. Um, I guess the only one would be ozone. Okay, and so ozone, knowing that it's a secondary pollutant, which means that it's not released directly by cars or industry, but it actually forms through something else. And so, kind of being familiar with this reaction scheme, not really to like regurgitate it, but just know that to form ozone, you need sunlight and really nitrogen dioxide. Okay, so this comes from vehicles. Okay, and so this is, remember, this is troposphere. So that is, ozone where we're breathing it in, and so that, hurts our lungs, our eye tissue, stuff like that. So it's the bad ozone. And then the next chapter we looked at good ozone, okay, to block UV radiation. Really these two requirements are needed. So sunlight breaks apart nitrogen dioxide, and then you have these reactions where this is a radical. Okay, so the term radical you should know. So explicitly, that first reaction really should be this. Okay, so that means that you're breaking apart a bond in NO2, and so these with dots are radicals, sometimes called free radicals. Okay, they're just, this dot means that there is an unpaired electron. Okay, so when you form a bond, like if you're breaking this bond, it's like saying that one of the electrons is going that way, one is going that way. Okay, so then you would end up like that for this particular bond. Okay. Okay, so these are radicals, which means they're going to look for something else to react with to form back to a molecule. Okay. And then indoor air pollutants, I guess really not too much I would ask related to that. Maybe a question about, kind of a giveaway question. Are you safe breathing air indoors or something like that? If air quality is horrible outside, are you safe staying indoors? Or are you free from any danger staying indoors, kind of thing? So it's better, potentially better indoors, but if you're smoking, if a lot of people are smoking inside, plus painting and all these other things indoors, maybe you'd be better outside. Okay, so being aware that there are such things as indoor air pollutants. I think just knowing that and kind of applying that concept. Okay. Um, Green chemistry could be a definition. And so green, so this essentially right here, so this sentence, so green processes, they use less energy, create less waste, require fewer resources, and if possible, use renewables. Okay, and so, just some examples here, but, nothing more than maybe a definition question. Okay, so anything about chapter 2? Any questions? Okay. All right. So the last one, I want to on Wednesday leave more time. I know chapter 4 is where we started the calculations, so that'll take maybe a little more time. So let's get through chapter 3 yet here. And so this is radiation from the sun. So this is now looking at ozone is good. Okay. Whereas chapter 2, ozone is bad, was the message. And so it's just in different regions of the atmosphere. Okay, so radiation. So knowing the, I guess, waves. So behavior of waves. So just definitions of what is a wavelength. Okay, and what is the difference between a wavelength and a frequency. And so this equation is really important. So that would be something I would jot down on my cheat sheet, if you will. Okay, as well as this. Okay, if you put it either one, you're going to get the right answer. So it could be that or that. Even if you abbreviate it as 3 times 10 to the 8th, it's cool. Okay, and so with this equation, you can convert. If I give you wavelength, then you can calculate frequency, right? Or vice versa. So it's just rearranging that equation where you're just dividing by whatever I'm giving you, okay? So converting between back and forth, knowing wavelength, frequency. Frequency is given in units of like reciprocal time, or hertz if it's seconds to the -1. You should know this range for the electromagnetic spectrum. So not these numbers, but know this is increasing as I'm moving my cursor here. I'm going from increasing energy, or to increasing energy. So gamma rays, whole lot of energy, radio waves, low energy. Okay. And also you can say that it's decreasing wavelength. Okay, so you should know that E is proportional to frequency, or E is inversely proportional to wavelength. Okay, and then the equations are these ones. Okay, where H is that other joule seconds. Okay, so that's the other constant. Okay, and that's your speed of light again. Okay, so you might have to calculate the energy based on if I give you frequency, wavelength, or you may just have to apply it. Like, what is, order? I think I had a question on the prac there, the former, one of your earlier midterms. What's arrange these in order of increasing wavelength. Okay, and then it would be like visible, IR, microwave, radio. Okay, so increasing wavelength. So read the question really carefully, what I'm talking about. Okay. And then as far as the visible range, you should know that the highest wavelength is at the red end. Whoops, I forgot yellow. Okay, Roy G. Biv. So this is the longer, so like 700-ish nanometers. And this is down at the 300-ish nanometers. Okay. And so at this end, this is where UV is. At this end, this is where IR is. Okay. And then this is visible. All right. So those are kind of the only numbers I'm going to have you kind of know roughly. Okay. And then converting. So this is then where the whole metric unit conversions came in. So all the way from, wow, where do we have it? So the base unit, and then we had deca, hecto, kilo, and then mega, tera, and giga. Okay, so we've got, if this is just one, that's 10, 100, 1,000, and 10 to the 12th. Okay, so you should know all the way to giga as far as like increasing size. And then it's deci, centi, milli. That's 0.1, 0.2, or 0.00. That. And then we had micro, nano, and then pico. Okay, and so you should know this. We talked about, I think we did, angstrom fit kind of in between, so that's 10 to the minus 10. So it's kind of right in there. Okay, so an angstrom is this, an A with a little degree above it. Okay, so that's 10 to the minus 10 of the base unit. Okay, so that would be, let's say, for meter. This would be for meters. Okay. That's especially just for length. Okay. All right. Yeah, quantization is not going to be a huge thing. I guess just the term. Yeah, not even. Yeah, it's kind of way beyond the scope of this class. So yeah, really nothing from, these. Yeah, a calculation like this is important, like energy of radiation, but nothing really. I won't talk about quantized anything. And then, yeah, so these types of UV radiation, so you should know, not really per se these numbers, but you should know that UVA has, I don't know what it's doing. UVA has the longest wavelength. Okay, so that means that it has the lowest energy. And then UVC has the shortest wavelength, the highest energy. Okay, and so UVC, so really this slide is really key. Okay, knowing that it's really dangerous, but it's really absorbed totally by ozone and oxygen. This is going to react just with ozone. And then this kind of doesn't react with very much, so it's going to be most of what is hitting our skin. Okay, so UVA, UVB is what you want your sunscreen or sunglasses, whatever, to protect you against. Okay. And then what effect UV radiation has on molecules. So it actually has enough energy to break apart bonds. Okay. Yeah, maybe a question like this of, why, um, African Americans have lower incidences of skin cancer. It's kind of, the melanin in their skin gives natural protection versus Caucasians. So, maybe explaining this. Although, the exam will be multiple choice, so the answer will be there in front of you anyway. So, but something maybe where you again interpret some data. Okay. Yeah, so UVA goes all the way, below the epidermis, so into the dermis or below even. So that's the danger of it. So this is why they figure it causes more skin cancer. Okay. Yeah, not so much. Yeah, the UV index, again, not knowing the numbers really, but knowing maybe the colors. So it goes green, yellow, and then into the red, getting more into, purple is, the worst kind, or, the most dangerous for your skin. So 11 plus. So maybe knowing the range, the number range that goes from 1 to, and then the highest is 11 plus. And these are kind of the colors. Um, the ozone layer, knowing it's in the stratosphere is good enough, really. Not so much really the measurement here. And then, yeah, the big topic of this chapter then was really Lewis structures. So knowing how to draw Lewis structures. If it's just an element itself, like what's the Lewis structure of chlorine? Atom. Okay, it would just be, it's in group 17 or 7A. So there's 7 valence electrons. So you just literally put 7 dots around it. Okay, so you might have just individual atoms or molecules. Okay, and then you add them up, and then remember, join it with singles, and then go all around the outside. And then if there's any left, they go around the central atom if there are any. Okay. You should know the exceptions to the octet rule. Okay, so carbon, nitrogen, oxygen, fluorine must have 8 electrons around them. Okay, but then if you have like group 13s, they can have less. And then anything third period and beyond can have more. Okay, like sulfur, phosphorus, etc. Okay. The Chapman cycle, I'm not going to ask you to reproduce this, but you should be familiar with, what happens when we say UV light is absorbed by oxygen. What happens? So it breaks that apart to give you radicals. So you've got 2 oxygen radicals that then combine with oxygen to form ozone. Okay. And so this is a natural cycle. So then, ozone can react with oxygen to give back your oxygen, and then it kind of starts again. Okay, so I guess, being familiar with the general reactions, where you've got one reaction is absorbing the lower of the wavelength, right? So this is the smallest wavelength, means the highest energy is needed to break apart oxygen, because remember, it is a double bond. So you need more energy to break that apart than you do this one, right? So that's ozone. So here you've got, remember resonance forms too. So, that one, etc. Okay, so this is like a 1.5 bond. It's between a single and a double. This is a double, so it's a stronger bond, which means you need a lower wavelength to break it apart. Okay. And so you've got that one going on, and then you've got this one where ozone is being broken apart. So that doesn't take as low a wavelength. So it doesn't take as much energy, if you look at it, to break apart ozone into oxygen and O. Okay. So yeah, so kind of no, it's multiple choice. So the question would be kind of related to these individual reactions and this wavelength versus that one. Like to break apart ozone, does it take this one or that one? Okay, and so you're just looking for what is the higher of the two as far as wavelength, because that means it's less energy required. Okay, so something to that effect. Um, and then, yeah, this, is describing what radicals are. Just, I guess, be familiar with the term in case there's a definition. Okay, and then, yeah, what happens when, this is, again, this is a natural cycle. So Chapman cycle is natural. This is what happens when we put in CFCs. So what are CFCs? You should know. And then what happens when UV light hits them? They break apart a carbon-chlorine bond because that's going to be weaker. So remember, as you go down a group, the bond strength is weaker. Okay, you just have larger orbitals that overlap. So this would be the weaker bond between CCl versus a CF. So that's going to release this. And now these reactions can happen. So that reacts with ozone. And you don't really have to know these products really per se, but just know that a chlorine radical reacts with ozone, okay, and effectively takes it out of the atmosphere. Okay, and so that's why we can have a hole in these ozone layer. Okay, and so this is the smoking gun evidence. So as chlorine in the stratosphere goes up, ozone in the stratosphere goes down. Okay. And then this one also is an important slide. So why over Antarctica? Why not so much in the North Pole? And it really has to do with the temperatures. So this is kind of the average annual temperature in the Arctic. And PSCs are essential for destroying the ozone hole. So these reactions occur on ice crystals. Okay, and so if you don't have many months where you form those ice crystals, then these reactions really don't happen so much. But if you look anywhere between like October to May, like even right now, you still have polar stratospheric clouds in the Antarctic. Okay, so you still are depleting ozone even now, whereas you're not in the North Pole. Okay, your temperatures are higher. Okay, so this is an important slide as well about kind of why or how it takes out the ozone hole. You should know about the Montreal Protocol. It just was, was designed to stop production of CFCs, and then, people listened, and it fell off pretty sharply afterwards, and then, things started to improve, but it's taking a long time to still improve the concentration of ozone. And then, maybe what some alternatives are. So be familiar with HFCs. So you're just replacing a chlorine with hydrogen. Okay. And that, for obvious reasons, you're then not going to break apart any chlorine. Okay. But the problem with that is that they're greenhouse gases. Okay, so this works as far as it's not kicking out ozone or destroying ozone, but now it's a greenhouse gas. So climate change is affected by that. Okay. Sunscreens, I'm not going to ask so much about how they work, because that's really kind of beyond the scope of this class. Yeah, I really won't talk too much. It's got particles in them that kind of absorb or scatter UV. So as far as that's probably as much information. They either scatter or absorb UV radiation. Okay? So it leaves your skin alone. Okay, so any questions about chapter 3? So that's as far as I wanted to get to today. And then on Wednesday, we'll go through chapter 4, which is where we got our mole calculations, all that fun stuff, where that occurred. And then chapter 5, I guess chapter 4 is also shapes of molecules as well. So 4 is a pretty key chapter. And then chapter 5, we were talking about energy, really. So just those few concepts. Okay, so any questions then about anything before we sign off today?